Hey, hello everybody. This is the first supplement for week 3. We might have a second supplement or we might not, just depending on how far we get in Wednesday's class. But the plan for this supplement is to cover section 4.14.2. So in yesterday's class, we covered 14.1 and then jumped to 14.3 and started that on partial derivatives. We skipped over 14.2 and we're going to fill in that gap today. So this is some kind of somewhat technical background material, not super important for the remainder of the course, but it's material that we really should discuss. Okay, so 14.2 on limits and continuity, and we're going to start with limits and continuity of functions of two variables. So two inputs, one output. Okay, so let's start with a definition. Let f of xy have domain D, including a neighborhood, in other words, an open disk surrounding the point AB. Then we say that the limit of f of xy as the point xy approaches the point AB is L, a real number, if the following is true. If it's true that for each epsilon bigger than 0, there exists a delta bigger than 0, such that if xy in the domain and the distance from xy to AB from the point that we're looking at right now to the limiting point AB, if that distance is less than delta and also positive, so xy is not the point AB, but is less than delta away from the point AB, then absolute f of xy minus L less than epsilon. This should look very similar to the kind of Calc 1 definition of limit, where we just said if absolute x minus a is between 0 and delta, then absolute f of x minus L less than epsilon. So this is just a perfect two-dimensional analog of that one-dimensional idea. If the limit exists, then we write the following: limit as xy goes to AB of f of xy equals L, a real number. Again, I'm stressing here, we wouldn't always write, in the real numbers, but I'm just stressing here that this L is a limit of the function. It's related to the output of this function f, and the outputs of the function f are real numbers. They're not vectors. Again, because we're in chapter 14, looking at multivariable functions or functions of several variables, rather than in chapter 13, where we were looking at vector functions. Okay, so schematically, we can think of this kind of in two different ways. And again, I grabbed these pictures from the book because the book does a much better job of drawing these than I could. So the first schematic that we have up here, we have an XY coordinate plane representing our domain. This blob here, this orange blob, is our domain. We have some point AB that's our limiting point that we're interested in. We have some disk of radius delta surrounding AB, and we have some point xy in that disk. And our claim is that when we fix an epsilon, we can choose a small enough radius for this disk surrounding AB, such that if xy is in that disk of whatever radius we pick surrounding AB, then the output, f of xy, will be within epsilon of the desired limit, L. So between L minus epsilon and L plus epsilon. So this is the domain out here, and this is the range, so to speak, over here. The inputs are over here on the left, and the outputs, or just the output, is over here on the right. And of course, we can visualize this three-dimensionally as well. We can think of the graph of our function in 3 dimensions as being a surface, where again, the xy plane is representing the inputs. It's representing the space with the domain in it. And then the height of each point above each xy coordinate is that height is the function output. So this graph is a surface in 3 dimensions, and we're saying that when we have a small disk surrounding AB, the outputs for those inputs, in other words, the heights of the points on this surface, are within epsilon of L. So our inputs are in this disk, and our outputs are along the z-axis here. And we see that if we want our outputs to be within epsilon of L, we can choose a small enough delta that a disk of radius delta, that a filled in circle of radius delta, using that as the restricted domain for the inputs, will yield outputs that are no further away than epsilon from our limit L. So again, if this is completely analogous to the one-dimensional example, if that's not ringing a bell, take a look back at I believe chapter 3 in Stewart Calculus. Take a look back at the precise definition of a limit, and you can see, actually it was chapter 2, sorry, but to take a look back at the precise definition of a limit in chapter 2, and you can look at the one-dimensional case and compare it to the two-dimensional case. Okay, let's look at some limits here. Now, the definition of the limit that we're working with is very similar to the definition, again, from chapter 2. However, we're going to see that there's a bit of nuance here in the actual calculation. So when we actually go through and try to compute limits, we're going to have to be a little more careful. So let's take a look at this first limit here. Limit is xy goes to 0, 0 of x over x cubed plus y cubed. So of course we note that, well, as xy goes to 0, 0, the numerator and denominator both seem to go to 0. If I just naively thought, what happens if I plug in x equals 0 and y equals 0, I get 0 over 0. We haven't discussed continuity yet, so we really ought not go just plugging things in right away. But if we just kind of thought, I wonder if I could do that, I see even if I could do that, I get 0 over 0. I have to do something a little more, a little different here. Okay, so what's one thing I could do? Well, my question is, what happens to these heights whenever I have points that are in some disk, in some neighborhood close to AB? Well, I could have points that are in this disk, let's say up here, and I could choose certain points. I could say maybe I'm interested in points, I'm interested in points where x equals a and y is allowed to vary. Or maybe I'm interested in a different subset of points where y equals b and x is allowed to vary. Or maybe where I'm kind of coming in along, say, a 45-degree line like this. I can imagine approaching AB from actually lots of different directions, actually infinitely many different ways. These are a few straight lines, but I could also choose a path that maybe looks like a quadratic, or even some kind of crazy thing. You know, it could go all around in here as it works its way toward AB. So this is as opposed to the 1D case where I could really only approach the limiting value from the left or from the right. That's about as much variety as I could get. Here I can get essentially infinite variety. But let me look at a couple of these paths and just see what happens. So what if I were to approach along a path, say that looks like 0, y? And here we'll take y being not equal to 0. So here I'm setting x equals 0, and I'm approaching along the y-axis. So my point of interest is 0, 0. And again, this is just representing kind of the domain space here. And I'm saying if I take x to be 0, then I'm approaching along a path, something like this, either from the positive y-axis going down towards 0, 0, or from the negative going up towards 0, 0. So if I look at points on this path, 0, comma y, where y is non-zero, again, we don't want to plug in 0, 0, so we don't want y to be 0. Well, here x is 0, y is non-zero. Let's maybe call this f of xy. So of course, f of 0, y is going to be 0 over 0 plus y cubed. That's 0 over y cubed. Note that this is not 0 over 0 because y is non-zero. This is 0. So my function output is actually 0 everywhere along this y-axis. Well, if the function is just a constant 0 along this y-axis, then of course, as I approach 0, 0 along this y-axis, the limit, at least from this perspective, ought to be 0. I just have a constant function everywhere but at 0, 0. It seems that it's suggesting the limit is 0. Let's look at another method of approach, though. We could approach, say, along the x-axis instead. I could approach along the x-axis like this, setting my y-coordinate to 0, looking at a non-zero x-coordinate, and then letting that x value go to 0. What happens here? F of x comma 0 is going to be x over x cubed plus 0 cubed, or this is 1 over x squared. What happens to this as x goes to 0? This actually shoots off to infinity. We get a smaller and smaller positive number on the bottom. That shoots off to infinity. So it seems like along the green path, I have a suggestion that my limit in some sense ought to be infinity from the perspective of the green path, but from the perspective of the blue path, my limit ought to be 0. These are clearly not equal. And this is kind of analogous to in Calc 1 when we said sometimes we have a left-hand limit and a right-hand limit that don't agree. And in that case, the limit doesn't exist. And that's the case here as well. I found two paths. Along one path, that as I approach 0, 0 along that path, I seem to approach a certain limit, maybe 0. And along another path, as I approach 0, 0 along that path, I approach a different limit from my outputs, say infinity. That's enough to show the limit doesn't exist, that I found two paths that contradict one another. Okay, let's look at example 2 here. Limit as xy goes to 0, 0. As an aside, we go to 0, 0 a lot, basically for convenience, because it's kind of an easier point to limit to. So for these examples, we pick 0, 0 as our limiting point quite often. Okay, so limit xy goes to 0, 0 of x squared y over x to the 4th plus y squared. Now here, let's try the same trick. Let's see, again, I could pick lots of different paths to approach 0, 0 on, but let's try along the y-axis, then along the x-axis, and just see what happens. So along 0, y, what happens? Again, I'll just always call this function here f. Well, f of 0, y, when x is 0, y is non-zero. I get 0 in the numerator. I get 0 plus y squared. So this isn't 0 over 0. It's 0 over y squared. That is 0. So along the y-axis, as I approach along the y-axis, my function is just a constant 0 there. Of course, that limits the 0, and that suggests that the limit from this perspective ought to be 0. What happens as I approach along the x-axis? f of x comma 0 gives me 0 in the numerator again, but now I get x to the fourth plus 0. This also is 0. Again, it's not a 0 over 0 because x is not 0. It's just a 0. I approach along the x-axis, I approach along the y-axis. In both cases, I get 0 as the output. Does that mean necessarily that my limit is 0? Well, not necessarily. Remember, there's not just two paths along the axes that I could approach along. There's a ton of different paths. There's infinitely many. I could approach along a bunch of different straight lines, but also curves and all kinds of crazy, parametric curves in 2 dimensions. So it's not enough for me just to say that the limit kind of, in a sense, agrees, or there's consistency between the approaches along the 2 axes. I need to do something more general than that. Okay, so let's take a look then. Okay, so the first important point is we have not proven. Let me write this down. Have not proven the limit is 0. That's a very important point. The limit might be 0. It really can't be anything other than 0, but the limit might be 0 or the limit might not exist. So what's another thing we could do? Well, we could either try to prove the limit is 0, or we could try to search along a different path and see if we can come up with a contradiction along a different path. So let's take a look along a different path. In this case, we're going to look along the path y equals x squared. So again, we have our domain, x and y. We checked as we approach along the axes, and in both cases, we got agreement that from each of those perspectives, the limit seems like it's 0. Along the path y equals x squared, what do we get? If we again get something that suggests the limit is 0, then maybe I'll start trying to prove the limit is 0. But if I get something that's not 0, then I've generated a contradiction. So along y equals x squared, what do I get? F of x comma x squared. And again, take x not equal to 0, and therefore y is not equal to 0. So when y is x squared, I get x to the fourth on top, and I get x to the fourth. Every once in a while, OneNote really, really wants to turn my 4s into 9s, and I'm not sure why. But y squared is x squared squared is also x to the fourth, and this is 1/2. X to the fourth over 2x to the fourth. For x not equal to 0, the x's divide out and give me 1/2, which is clearly not equal to the zeros from up here. And in fact, if we approached along the curve y equals cx squared, we would end up with a cx to the fourth over what? 1 plus, and then y squared here gives us a c squared x to the fourth. We'd have c over 1 plus c squared. This could actually be any number between minus 1/2 and plus 1/2 for this output. So depending on which value of c we pick, we could kind of suspect that the limit is any number between minus 1/2 and plus 1/2. And as an exercise, check this. So check that the outputs of c over 1 plus c squared are indeed in the interval minus 1/2 to plus 1/2. Little Calc 1 exercise, just to kind of review some things about maxes and mins and horizontal asymptotes, things like that. So as an exercise, check that that is true. But indeed, we see that along this parabola, y equals x squared or y equals cx squared, we get something that contradicts that the suspicion that the limit could have been 0. So this limit also does not exist. Okay, so let's take a look at example 3 here, limit as xy goes to 0, 0 of xy times x squared minus y squared all over x squared plus y squared. Again, if we just kind of naively thought, what happens if I plug in x equals 0, y equals 0? I get an indeterminate form, 0 over 0. So what can I do here? Well, here I'm going to make use of an inequality. I'm going to note that the absolute value of x squared minus y squared is less than or equal to x squared plus y squared. So let me just come over here and prove this. So let's look at a couple cases. Case 1, if x equals y, then obviously our statement is just x squared minus y squared is 0. It's just that 0 is less than or equal to x squared plus x squared, 2x squared, which is obviously true. Case 2, if x is not equal to y, without loss of generality, we can take x squared bigger than y squared. If x is not equal to y, either x squared is less than y squared or x squared is bigger than y squared. I suppose there's an x equals plus or minus y issue, but that's essentially that's covered under this case up here. I'll leave it as a minor exercise to see why that's true, but without loss of generality, we'll take x squared bigger than y squared. Why can we do that? In other words, we don't have to do the case x squared bigger than y squared and also do the case x squared less than y squared separately. Well, because if we exchange x and y over here, we get exactly the same statement. So whichever one has the bigger square, we just label it x, and then the other one we label y, whatever number. Of course, x squared minus y squared, if we flip that, that's y squared minus x squared. The negative pops out, but the absolute value gets rid of the negative. And the x squared plus y squared, everything commutes just fine. So without loss of generality, we'll take x squared to be bigger than y squared. And we note that absolute value of x squared minus y squared, which is because x squared is bigger than y squared, x squared minus y squared is bigger than 0. So the absolute value of x squared minus y squared is just x squared minus y squared. The absolute values just go away because we're absolute valuing a positive number. This is obviously less than or equal to x squared minus y squared plus 2y squared. If we add something non-negative, that can only make the thing bigger. And x squared minus y squared plus 2y squared is just x squared plus y squared. So the interesting case we have shown. Well, if absolute value of x squared minus y squared is less than or equal to x squared plus y squared, absolute value of x squared minus y squared over x squared plus y squared is going to be between 0 and 1. So let me look at my function. We'll call it f here. And in fact, I'm going to look at absolute value of f of xy. Well, this is what? It's absolute xy times absolute x squared minus y squared over x squared plus y squared. I don't need absolute values on the bottom because that's non-negative already. And I know that the absolute value of anything is bigger than or equal to 0. But I also know that this factor from this inequality is less than or equal to 1. So this whole expression is less than or equal to absolute value of x times y. So I have that 0 is less than or equal to absolute value of f of xy is less than or equal to absolute value of x times y. But I note that as xy goes to 0, 0, absolute xy goes to 0. It has to, right? X is getting closer to 0, and also y is getting closer to 0. Their product in absolute values has to get closer to 0. But my squeeze theorem applies here. And this says the absolute value of f of x, y goes to 0 as xy goes to 0, 0. And if something in absolute value goes to 0, then the thing itself has to go to 0. So which implies f of xy goes to 0 as xy goes to 0, 0. And we can say that this limit is 0. So what did I do? I bounded my function above. Well, I bounded it below by 0 and above by something that went to 0 and applied the squeeze theorem. So it's often the case that if that when we're evaluating limits in 2 dimensions, we have to be maybe a little bit trickier, use maybe a little bit more of a subtle argument to prove our limits. It's a little bit less kind of, sledgehammer like, or a little bit less turn the crank as many of the limits in Calc 1 were. Okay, let's look at this limit. And again, let's just naively think, what if we plugged in x equals 0 and y equals 0? Again, that's our limiting point. And we get 0 in the numerator, and we get square root of 4 is 2 minus 2 in the denominator. So we get 0 over 0 in indeterminate form. Here again, xy is going to 0, 0. But I do notice that everywhere that x and y come up, they come up as this kind of couplet, I suppose, x squared plus y squared. So whenever I have a point xy, I could represent that in polar coordinates as r theta, where r squared is x squared plus y squared. And pretty clearly, as x and y go to 0, 0, regardless of what path they take, if they're approaching 0, 0, my radius also must go to 0. Can I take this 2-dimensional limit and kind of massage it into a 1-dimensional limit? So really what I'm interested in is what happens for the limit as r goes to 0 of, well, x squared plus y squared is r squared on the top over root r squared plus 4 minus 2 on the bottom. So all that I've done is change the variable. I've used polar coordinates to kind of help me out, to help me visualize things, but I can see very clearly this works out algebraically as well. And this might be a type of limit that I recognize from Calc 1. I multiply by the square root of r squared plus 4 plus 2 in the numerator and denominator. And then in the denominator, I have a difference of 2 squares. I have square root of r squared plus 4 squared is just r squared plus 4, and then minus 2 squared minus 4. I notice that my plus 4 and minus 4 cancel out, and my r squareds then divide out. And here I have limit r goes to 0 of square root of r squared plus 4 plus 2. And now we're in kind of 1 dimension, so we know all of these limit rules that apply. We can just essentially plop the 0 in there. Square root of 4 is 2. 2 plus 2 is 4. So the value of this limit is 4. Okay, coming down to example 5. Here we have limit xy goes to 0, 0 of x squared plus y over root x squared plus y squared. Again, an indeterminate form if we were to just naively plug in x and y equals 0. So what approach could we take here? Again, let's take a look at what happens along the axes. So along the axis, say x comma 0, taking x not equal to 0. So when y is 0, I get f of x comma 0 equals x squared over, and then we have square root of x squared. Let's actually take x bigger than 0 just so we can approach just from the positive side. Square root of x squared would be absolute value of x, but this way we don't have to deal with absolute values. And see f of x comma 0 equals x. And then to approach the point 0, 0, we have to let x go to 0. So this, of course, goes to 0. What if I approach along the y-axis instead? 0 comma y. And again, we'll take y bigger than 0. F of 0 comma y, when x is 0, what do I get? It's going to be y over square root of y squared, or that's just y, is 1, just the constant 1. The y's divide out. And then again, to approach the point 0, 0, I have to take y goes to 0. But of course, for the constant function 1, as y goes to 0, that doesn't affect the output. It's still just 1. I've approached along the two positive sides of the axes, and I've shown that on one hand I get 0, and the other hand I get 1. These are not equal. This limit does not exist. Okay, so we've talked a bit about limits in 2 dimensions, and I think that we see it's quite a bit more complex than limits in 1 dimension, mainly because of this issue that we can approach along infinitely many different paths. Now let's look at the 2-dimensional analog of continuity. Function f of xy is called continuous to point AB if limit as xy goes to AB f of xy equals f of AB. In other words, if I can plug in x equals a and y equals b into my function and get the output of the limit, that's what we mean by a function being continuous. Very analogous to single variable calculus. Also an important note, as in single variable calculus, combinations of continuous functions in 2 dimensions. So if we take continuous functions and we add, subtract, multiply, or divide them, provided we're not dividing by 0, those combinations are continuous. And also, polynomials, rational expressions, power functions are continuous on their domains. So all of those nice limit laws apply. Things like limit of the sum is the sum of the limits, and limit of the square root of something is the square root of the limit of something. Again, as long as we're acting on domains and things like that. But so all of those nice limit laws from Calc 1 apply to the 2-dimensional case as well. Okay, so example 6, is the following function continuous at the origin at 0, 0? F of xy is defined to be sine of xy over x for xy not equal to 0, 0. But of course, if we try to plug in 0, 0 here, we get an indeterminate form. So we have a piecewise defined function where we say f of 0, 0 equals 1. Is this function continuous at the origin? What do I need to know? I need to know whether it's true that limit xy goes to 0, 0 of sine of xy over x, is that equal to f of 0, 0, 1? Is this limit 1? Well, let's just figure out what this limit is. I know that something like limit as x goes to 0 sine of x over x, that's a recognizable limit. That's 1. That's kind of a standard limit that we've come across in Calc 1 before. Again, go back and review that in Chapter 2 if that doesn't sound familiar. So we recall this limit. And I say this kind of looks somewhat similar, right? Sine of xy over x. I mean, if that y wasn't there, I would just be able to say right away that this is 1. But the y is there. What does that actually do? Well, one thing I can note is that I can actually multiply by a y in the bottom, and then I just have sine of xy over xy. I have sine of, let's say, w over w, where w goes to 0. Well, that's 1, right? So this kind of recovers my familiar limit, but I stuck a factor of y in the bottom. I better multiply by it on the top as well. Well, the limit of the product is the product of the limits, so that's going to be limit xy goes to 0, 0 of y is obviously 0, times limit xy goes to 0, 0 of sine xy over xy. Again, we could make a new variable, call it w or something, call it sine of w over w. As w goes to 0, that limit is 1. 0 times 1 is 0. And unfortunately, this is not 1. In other words, this is not f of 0, 0, which is defined to be 1. So we are not continuous at the origin under this definition. If instead of defining f of 0, 0 to be 1, if instead we had defined it to be 0, then yes, we would be continuous. But because the output at the origin is 1 instead of 0, and the limit as we approach the origin is 0, those two don't match up, and our function is not continuous at the origin. So the answer, as it stands here, is no. Okay, example 7, compute the following limit. Limit is xy goes to 1 comma negative 3 of this function x squared plus y over root x squared plus y squared. And note that in this case, we're limiting to a point x equals 1, y equals negative 3. I do note that this is just a combination of a bunch of continuous functions and power functions and so on. So I can use my limit laws here, and I can actually use continuity. When x is 1 and y is negative 3, everything works out nicely. Right? If I just were to think, can I naively plug in x equals 1, y equals negative 3 and get an output? Here, the answer is yes. I don't get something like an indeterminate form. So what am I going to end up with? Just 1 squared plus negative 3 over root 1 squared plus negative 3 squared. That's negative 2 over root 10. And that is simply the value of our limit. It's not because we just naively plugged stuff in because we wanted to. It's because we're leveraging now these ideas up here. Particularly this note. Really, this note is a theorem. And we didn't prove it, but really this note is a theorem that we can use. And we're leveraging that theorem here to make evaluating this limit much easier. But as long as our function is well behaved, nice and continuous, and as long as we're limiting to a point that doesn't cause any problems, it doesn't cause, say, an indeterminate form or dividing by 0 or something like that, we can just plug in and evaluate. Okay, now let's look at example 8. So here's an interesting an interesting question. We're jumping ahead a little bit here. Strictly speaking, this isn't fair game for section 2 because this includes partial derivatives. But since we've already introduced a bit of the idea of partial derivatives, we're going to finish up partial derivatives in the next class. I want to throw this in here in this section because it deals more heavily with limits than partial derivatives. But it is an important idea. Okay, so we've seen this function before. Obviously, this function has a problem at xy equals 0, 0. We're dividing by 0 there. So we'll define f of xy to be this function for all xy's that are not the origin, and we'll define it to be 0 at the origin. And our question is it true that the mixed partials fxy at 0, 0 equals fyx equal at 0, 0? So is it true that the partial of f, or sorry, that the partial of f with respect to x, or ddx, ddy, f of xy evaluated at 0, 0, is that equal to partial with respect to y of partial with respect to x, f of xy at 0, 0? Trying to use somewhat explicit notation here. Doesn't matter which order I do the partial differentiation. And again, we haven't, quite finished up the partial derivative section yet, so this might be something to kind of check back on a little bit later in the week. But I think this is a pretty approachable problem at this point. But I want to throw it in here with limits because it is a little bit more technical and a little bit more of a side note. Okay, so let's start by looking at the first partials. Let's start by looking at, say, df dx. So here we'll start with x, y being not being 0, 0. What is the x partial in this case? Well, df dx of xy is what? Well, remember, we treat y as a constant and x as the variable. We need to use the quotient rule here. So we have a bunch of stuff over the bottom squared. So x squared plus y squared all squared. And what is my quotient rule? It's bottom derivative of the top. And now when I say derivative of top, I mean derivative with respect to x. Let me make this top a little easier to differentiate. What I'll do is I'll multiply through my xy through these parentheses here. So I get what? X cubed y minus xy cubed over x squared plus y squared. So I have bottom derivative of top with respect to x is going to be 3x squared y, and then minus y cubed. Again, just treating y as a constant. So that's bottom derivative of top minus top, x cubed y minus xy cubed, times the derivative of the bottom with respect to x. The x squared differentiates the 2x. The y squared is treated as a constant. That constant term just differentiates to 0. And then let's look at df dy as well. Again, when xy is not 0, 0, doing df dy, we have a similar setup. We need to square the bottom. We get bottom derivative of top with respect to y now. So I get x cubed minus 3x y squared. So that's bottom derivative of top with respect to y minus top derivative of bottom with respect to y is 2y. Okay, now a tough question. What is fx at 0, 0? We might be tempted to do something like try to plug in 0, 0 into our fx formula to the left there, or take a limit or something, but we really need to approach this directly. Fx at 0, 0 is the limit as h goes to 0, f of 0 plus h, comma 0, minus f of 0, 0 over h. We really need to go back to first principles for this, because f is piecewise defined at 0. I noticed that by definition, f of 0, comma 0 is just 0. So what's f of 0 plus h, comma 0, or just f of h, comma 0? What do I get for f when I plug in y equals 0 and x equals h? And keep in mind, h is not 0 as it's limiting towards 0. That's one of the important conditions of our limit. Well, if the x coordinate is h, not 0, my denominator doesn't zero out. When y is 0, my numerator zeroes out. This is just 0. Okay, so the partial of f with respect to x at 0, 0 is 0. And for a similar reason, the partial of f with respect to y at 0, 0 is 0. As an exercise, fill in the details here. It'll look pretty similar to the one I just did. Okay, so I now have my x partial and my y partial. Now, I'm interested in whether my mixed partials at 0, 0 are the same. If I'm not being careful about what's being asked, I might actually try to compute my mixed partials, and that would be one heck of a mess. I don't need to compute my mixed partials, and in fact, I really don't want my mixed partials as functions of x and y, because that's really not what I'm looking for here. So what is f x y at 0, 0? Well, that means this. It means the y partial of this function at 0, 0. Or in other words, that means the limit as h goes to 0, the y partial means we vary y. So that's f of 0, comma 0 plus h, f x of that, because that's the function that we're inputting, minus fx of 0, comma 0 all over h. But wait, fx of 0, 0 is 0, so that just goes away. Fx of 0, comma 0 plus h, that's just fx 0, comma h. That's this function plugging in x equals 0, y equals h. Since I'm not going to use this function again, I'm just going to draw on it. So x equals 0 gets rid of this guy and this guy. So that term goes away. X equals 0 gets rid of, well, this whole second bit there. So I get a minus h to the fifth. And putting in x equals 0 gets rid of this bit. I get over h to the fourth. That's what fx of 0, comma h gives me. Let me move my equal sign a bit to the left to squeeze my limit in here. And I still have a 1 over h floating around this minus h to the fifth over h to the fourth is just what fx of 0 comma h gives me. And then times a 1 over h. All of my h's divide out, and this gives me limit h goes to 0 of just the constant -1. fxy of 0, 0 equals -1. As an exercise, show that fyx of 0, 0 equals +1. My mixed partials at 0, 0 for this function are not equal, but we're going to see a theorem coming up called Clairaut's theorem that kind of says, seems to suggest that mixed partials, maybe if we're not careful, we might think that it suggests they're always equal. But there's an important criterion attached to it. It says if something is true, then the mixed partials are equal. And this just demonstrates that that criterion, that assumption, is actually important. The mixed partials aren't always equal. They're only equal under the assumption of Clairaut's theorem. Okay, so now let's talk about limits and continuity of functions of 3 or more variables. Can we generalize the ideas that we just discussed to 3 or more variables? And my words are going off the screen a little bit here, so let me just fix that. Okay, so we have a new definition of a limit, but again, this should look very similar to the one we just introduced in the definition from Calc 1. This might even look more similar to the definition from Calc 1. So here, our definition, let f have a domain D subset of Rn, n can be 3 or more, and suppose it includes a neighborhood of the vector A in Rn. A has components a1 through an. Then we say the limit of f of x as x approaches a. Here we have a vector x being input, an n-dimensional vector. The n-dimensional vector x approaches the n-dimensional vector a. We say the limit of that is L, a real number, because the limit we're talking about an output of f. F gives a real number as output, but takes multiple variables as input. We say the limit of f of x as x approaches a is L, a real number, if it's true that for each epsilon bigger than 0, there exists a delta bigger than 0, such that if vector a is in the domain of the function and the length of the vector x minus a is between 0 and delta, strictly between 0 and delta, then f of x minus L, the real output of the function f for the input vector x, minus the real number L, the claimed limit, in absolute value is less than epsilon. A little side note, the first kind of absolute value looking symbol, this one here, represents the length of a vector in Rn, and the second here represents the absolute value. I mean, I guess it's kind of the length of a vector in one dimension. And again, if this limit exists, we write limit x goes to a, where x and a are bolded, they're vectors. It's a little hard to see in the subscript. F of x, where f is a scalar, but x is a vector, equals L, a real number. This probably looks even closer to the Calc 1 definition of a limit and notation for a limit, because we've just essentially replaced our input variables, our domain variables, with vectors. Okay, so let's look at this example, example 9, computing this following limit for a function of 3 variables, taking 3 variables as inputs and yielding a real number as L. So this is f of x, y, z here that we're looking at. Let's try our same trick as before. We have our domain space now is a 3-dimensional space. Oops, not z, x. It's a 3-dimensional space x, y, z. And let's take y equals 0. So we're in the xz plane. So we're going to take a subset of our domain and just consider the XZ plane. So we're going to consider points that look like x comma 0 comma z in our domain. Of course, as x and z goes to 0, we work our way towards this limiting point, the origin. So it's perfectly reasonable to stick a 0 there. I wouldn't want to stick a 1 there or something for y, because then I can't get arbitrarily close to 0, 0, 0. But by sticking y equals 0 in there, well, and of course, x and z not equal to 0, at least one of them not equal to 0, so that we are staying away from this point, right? An important criterion with all of these limits is that our distance away from the limiting point is positive. We're not at the limiting point. So it's kind of like a disk with a hole in the middle. It's a very important point, both in Calc 1 and in our discussions here. Okay, so what does f of x comma 0 comma z look like? Well, that's 0 plus 0 over, very importantly, something non-zero plus 0. That's 0 over number. That's 0. So anywhere on this xz plane, if my input lies in this xz plane, then my output is 0. And this, of course, goes to as x, y, z goes to 0, 0, 0. This goes to 0. It's just a constant function. So as I pick any curve in this xz plane that kind of winds its way towards the origin, as long as the output is in that xz plane and that curve winds around that xz plane, the output of f is always going to be exactly 0. So of course its limit is going to be 0. So from the standpoint of any path that stays in the xz plane that approaches the origin, the limit ought to be 0. If we check some other paths, do they tend to agree, or can we find a disagreement and therefore argue the limit does not exist? Let's check a different path. Let's check instead the path zero y. So here we're taking x equals 0 and z equals y. So x equals 0, we're in the zy plane, and we're approaching, say, something like this, right, along z equals y. A 45-degree line in the zy plane, and we're approaching the origin along there. And again, if we see that this is 0, that this would limit to 0, that doesn't prove the limit is 0. That just says that we have agreement so far, and we might have to do more work to prove the limit's 0. But does this show that? Well, if x is 0, and of course y not equal to 0, we are working our way towards the origin, but we're not there yet. If x is 0, these two terms go away. And then on the top, I have y times z, but that's really just y squared. And on the bottom, I really just have y squared plus y squared, 2y squared. Y is not 0, so this is actually just 1/2. So along this green curve here, the straight green line, anywhere along there, my function has constant output 1/2. Of course, this goes to 1/2 as x, y, z goes to 0, 0, 0 as we approach the origin along this line. Our function has a constant output, so of course its limit is just 1/2. So along one path or set of paths, I have a limit that seems to be 0, but along another path, it's 1/2. These are not equal. This limit does not exist. Okay, and then last but certainly not least, example 10, compute the following limit as x, y, z goes to 0, 0, 0 of x squared, y squared, z squared over x squared plus y squared plus z squared. Okay, so one thing we realize here is there's a lot of symmetry here. So there might be a lot of different approaches to this problem. But I do notice that x squared over x squared plus y squared plus z squared, I notice that my denominator is strictly bigger, right? Maybe not strictly bigger, it's bigger than or equal to my numerator. Y squared and z squared, unless they're both zero. I suppose x could be like one and the other two could be zero. But unless they're both zero, this denominator is strictly bigger than the numerator. And if y and z are both zero, but x is non-zero, then the numerator and denominator are equal. But I notice that the denominator is bigger than or equal to the numerator, which means this fraction is less than or equal to 1. And of course, this is bigger than or equal to 0. So I see that this x squared factor in the numerator over x squared plus y squared plus z squared is between 0 and 1. So what does this tell me? This says 0, of course, is less than f of x, y, z, which is x squared over x squared plus y squared plus z squared times y squared z squared. But this is less than or equal to y squared z squared, which goes to 0 as xyz goes to the origin. Y squared times z squared has to go to 0 as y and z both go to 0. But again, my function that I'm interested in taking the limit of is stuck between 0 and something that limits to 0. This limit must be 0 at the origin. Okay, so that wraps up our discussion for section 14.2. And again, on Wednesday, we'll come back and we'll finish section 14.3 on partial derivatives that we already started, discuss 14.4, and depending on whether we get through all of 14.4 on Wednesday, there might be a little supplement to wrap up 14.4, or we might finish everything in Wednesday's class.